Hi everybody. What I want to do in this video is talk a little bit more about Bose-Einstein condensation. So in the last video we talked about how as you get down to a very cold temperature you can start substantially filling the ground state. And in fact we came up with a approximation for how much you're filling the ground state as a function of temperature. So Einstein then predicted that you would get a new type of matter called a Bose-Einstein condensate once you got down very close to absolute zero. And the idea is that, when you start cooling things, you have particles, when they're fairly warm, separated. They have a de Broglie wavelength associated with them, but they're far enough apart that those wavelengths don't overlap. Then as you get below that critical temperature and things start getting very close together and their wave functions start to spread out, that the wave functions will overlap and you won't be able to tell individual particles. They'll look like one particle blurred out. So they're wave functions. You can't tell the separate wave functions. They're overlapping. Just looks like one big envelope. So Einstein predicted this in 1924. And in 1995, it was seen for the first time. So it took all that time to realize this dream of seeing this condensate that Einstein predicted. So it was first done by, three people close to the same time did it. Let me get rid of this. These were the first to do it. This is Eric Cornell, and this is Carl Wyman, and this is their apparatus. And you'll see here they have places, coils of wire. This is for magnetic fields, and we'll talk about that. They have mirrors, and we'll talk about how they did this in a second. Wolfgang Ketterle also did it at MIT. So Eric and Carl were at Gila in Boulder, Colorado, at the University of Colorado. And then Wolfgang Ketterle here in the center, he is at MIT. And he also did, I think Eric and Carl did it with rubidium atoms, and if I remember right, Wolfgang did it with sodium, but I could be wrong about that. But they all shared the 2001 Nobel Prize for that. I actually met them that year in Williamsburg, Virginia, at a conference, and I got to talking to Eric, and he ended up coming. He has a brother at the University of Iowa that teaches there, and he ended up coming here and giving a lecture on this. I think it was 2002 or 2003 that Eric was here. So how did they do this? This is the basic setup, and we'll talk about this in a second. So they have lasers coming from every direction, hitting and even up and down too, hitting your atoms, your gas, and they use these lasers to cool them off. And let's talk about that. So, how do you cool a gas down to near absolute zero? So it was done again in 1995 by the group in Colorado and at MIT. Gila is the group in Colorado, and MIT is where Wolfgang Ketterle worked. And both had the same procedure. So the first step is to cool it with lasers. And I know that doesn't sound right because you would think lasers might heat things up. But you have a laser here. Here's our gas. We shine a laser beam on it this way, and the laser beams, they make them fairly big, so the diameter is maybe a couple centimeters for a laser beam. And you have another laser going this direction. Laser going this direction. And then they have a mirror. So you'll put a mirror here to reflect it. So then it reflects the beam back again. So you have a laser beam going from every direction. Put another mirror here. So you get reflection back. And then we'd have one vertically coming from under, above, and a mirror up above that would go back. So you have beams coming in all directions. Okay, so how does that cool it down? So we have, here's our gas atom with its nucleus and its electrons, and here's a photon from the laser coming this way. A photon has a certain energy given by h times the frequency, and if that valence electrons has a state that it can go into that the energy difference matches that. So for example, let's say we have a possible transition from a 1s to a 2p. Then that photon has to have exactly that energy, right? Or the atom won't absorb it. But if it does absorb it, then it also gets the momentum that that photon has. Remember that photon has a momentum. So that slows down that atom. If the atom gets hit by lots of those photons, it'll slow it down. There's a problem with that, though, because the atoms are going with a fairly big velocity in this direction. You've done calculations, you know that molecules in the air are going around 500-600 meters per second on average. So what happens is you get a Doppler shift in that energy. Or you can think of it like this, that electron sees a different energy of that photon because of the Doppler shifting. So it might not make that transition. So you can tune that laser so that it will match the that energy as the atom goes towards it. Or you can do another thing. You can put the atoms in a magnetic field. So let's say this is the x direction. So that might be this direction. Let's create a magnetic field, a linearly changing magnetic field. And what does that do? Well, here's my transition 1s to 2p. You know, when you put an electron in a magnetic field, let's say the orbital angular momentum is 0, but there's still spin. So you get a branching of the energy, right? We get it here too in this one, I guess. So now, as the atom's going towards it, that magnetic field gets stronger and stronger, and at some point you'll hit it with a photon and it can make that transition. So that's one way to do it. So the lasers are continuously bombarding these atoms with photons, and you do this so that if the atom's going towards that, it gets absorbed by that photon, but if it's going away from it, it doesn't. Okay? So you're slowing these atoms that are going towards this laser are slowing down, going towards this side or slowing down, going towards this side or slowing down. So you're starting to trap them in a smaller and smaller region. And they're slowing down, so they're getting colder. Remember, 3/2 kT is an average energy for a ideal gas atom. So the temperature goes down as the energy goes down. So once you get them cold enough and slow enough, you'll put them in a magnetic field. And just a pure magnetic trap. Okay, so now that we have cooled the gas with lasers and a magnetic field and magneto-optical trap, then we're going to put them in a magnetic bowl. So we're just going to confine them with a quadrupole magnetic field, a rotating magnetic field, but we won't get into that. And actually, to do that, they pump them up into a another state. So the rubidium atoms have a valence electron in the 5s state, and they pump them up to the 5p state, and then they make a transition back down into a metastable state. So in there, so all these atoms, rubidium atoms, have the same spin now, and they put them in a magnetic field. And you guys know that if you're in a changing magnetic field and you have angular momentum, spin angular momentum in this case, you feel a force. And so the rotating magnetic fields in such a way that they basically go around in this bowl. And so they'll have a certain energy. They're still moving around, although a bit slower. And then what they do is use evaporation. So they lower the sides of the magnetic trap. And what that'll do is the ones that are moving faster can leave. So just like blowing on your cup of coffee, and the cold gas atoms leave first. And what's left is then a colder, everything else is moving slower. And they just slowly keep doing that. So, 300 microkelvins, 200 microkelvins, 100 microkelvins. And doing this, they can get down into the nanokelvins. And so this is a plot that was put in the paper by Cornell and Wyman. And this is a velocity plot of the rubidium atoms. So say velocity in the x direction, velocity in the y direction. And then the height is how many atoms with those different velocities. And I think they determine this by shining light through the gas. So of course that destroys it heats up the gas when they do that. So I think to make each of these plots, they have to do the experiment 3 times to get these 3 different plots. So they look at the optical properties of the gas. If the gas is moving faster, maybe less light gets through the gas. Or the other way around. So this is a plot at this I think was 200 nanokelvins. I don't have it labeled here, but you get a distribution of velocities. But as you go down to 100 nanokelvins, you can see close to 0, which would be in about the center of this, you get a lot of the atoms are barely moving. You still have a distribution outside here, but then as you go towards just a couple nanokelvins, you're a billionth of a Kelvin, most of them, they're just distributed around the 0 velocity. So I got this off the Hyperphysics website, this plot. So there you go. 1995, first discovered. There's a lot of applications. I'm not going to go over a lot of them, but we make atomic clocks with atoms, and these are the clocks we use to control our GPS satellites. And now most of us use the GPS. So maybe we can make better atomic clocks if we have colder atoms that are not moving. We can study things like gravity. We can maybe make rotational devices to measure rotation with these cold atoms. Also, we might use these for quantum computing. So the interesting thing is that you can have a macroscopic system. Now they can have thousands and thousands of these atoms moving together as a one quantum particle now, because that's what you have when you make this condensate. You have all the atoms moving together as one quantum particle because their wave functions all overlap. They're moving around at the same, basically 0 velocity. So you can, have a macroscopic system that's obeying quantum mechanics, and you can study quantum theory then with a macroscopic system using this. So you might be able to use condensates to make nodes for quantum computing. So there's a lot of people working on it. There's a researcher at Harvard that has stopped a light beam in this condensate and then let the light beam go, and you don't lose the information that was in the light beam. So there are applications, and people are, they can make these quantum systems now, these condensates, a lot easier now than when they first started. So here's a picture of one in the chamber. So it looks like it's glowing, it's scattering light. So it's because you have all the particles basically in close to one position here. So Einstein predicted this in 1924, and it took a long time to be able to produce this, but who knows where we're going to go from here with this stuff. So if you want to know more, there's a lot of YouTube videos out there about Bose-Einstein condensation. I'd be happy to talk to you more if you want to know more details about anything we talked about.